Hello, everyone, and a warm welcome from the Canadian Institute for Cybersecurity. I'll be your host. My name is Sumit Kundu. I'll be your host for the next couple of hours. And today's session is titled Canadian Institute for Cybersecurity 2024 Dataset Creation at the University of New Brunswick. We have lined up some amazing group of speakers for you over the next couple of hours. But before we get into the presentation, just allow me a few minutes to give a very quick introduction of, what it is that we do. So, like I said, we are Canadian Institute for Cybersecurity, located here at the University of New Brunswick. A bit about our geographical location. We are located in the province of New Brunswick, which is one of the four provinces of what forms the Atlantic Canada here in the country. A bit about our flag. Our flag shows the importance of maritime activity here in the province, and also our history and connection with the continent of Europe. In terms of business, we are big in lumber. If you talk about numbers, lumbers constitute, somewhere close to, 10% of the province's GDP. We are big in potato farming as well, so as home to, companies like McCain and Cavendish Farms. While these industries have been the backbone of the province historically, we have been making some advancement in the field of information communication and technology, and in the space of cybersecurity as well. This is the beautiful University of New Brunswick campus here in the city of Fredericton. It's a beautiful campus, and by the way, it's a place for many firsts as well. It's one of the first public university here in the country, and it is the first English language university, in the country. And we are also the first university to launch a computer science faculty back in the year 1990s. While these are some very important historical facts, but the University of New Brunswick is big on innovation and entrepreneurship as well. If I can mention a couple of examples, one example that comes to my mind is Bosiron Security, a company that was started by researchers of UNB, and now has been working as a full-fledged company here in the province, and has customer across the continent. This is us. This is the team here at the Canadian Institute for Cybersecurity. The institute was founded in 2017 by our founder and our director, Professor Äì The Rabbani, who's also Canada, who's also cybersecurity research chair here in Canada. Other than that, we have two more research chair, Mastercard research chair and an NB Power research chair. When it comes to number of people, we are a little over 100, which includes our postdocs, our students, our staff. We are big on industry partners. We have close to 5 active members in the industry, which includes members from both the private and the public sectors. Right since the time the institute was founded, like I said, we are big on partnerships. We have founded 15 MOUs. Rather, I should say we have co-signed 15 MOUs, and co-founded 2 consortium. One of that consortium is the National Cybersecurity Consortium, which was a consortium between 5 university, which came together, got a lot in the federal funding. And it's a good example of how, the private sector and public sector came together and did some really critical, research in the space of cybersecurity. A bit about our strategical priorities. Like I mentioned in the like I mentioned in the earlier slide, we are big in partnership. We partner with all sort of companies, small scale, medium scale, the private sector organization and the public sector organization, and we help them solve some of their cybersecurity problems and challenges from a research point of view. We are big in growth as well. And when I say growth, I just don't mean in terms of growth of the institute. We also contribute to the growth of the country in terms of the cybersecurity. So how we do that is we provide our research, we provide our talent, which enables the cybersecurity system here in the country. We are big in research. Rather, I should say our bread and butter is research. Most of the comprehensive research is done with our industry partner. One of our main focus is also to develop and offer training programs to meet the true cybersecurity needs of both the public and the private sector. So we have long-term training and short-term trainings. Our short-term trainings would be a typical cybersecurity 101. Our long-term trainings would be, let's say, somebody is planning to do their PhDs in cybersecurity. Institute is the place for them. We also have what you call is a Masters of Applied Cybersecurity program. It's a very fast-paced program. In that program, we look for a really mature student, somebody who has done a bachelor's in technology, a few years of experience in the industry. We put them in this very, very fast and rigorous course, and once the course is over, they join the workforce here in Canada. We do a lot with respect to our knowledge sharing and community. If you're somebody who's a student, who's a researcher, or who's somebody who wants to, keep up their knowledge base with respect to cybersecurity, I would urge you to visit our website. We upload all sort of content there. When it comes to knowledge sharing, we also have a monthly webinar. So we organize 2 webinars every month in which we, invite leaders from academia and from industry to come on our webinars and, share their knowledge and share their wisdom for us. So if you never want to miss an opportunity to attend one of those webinars, please follow our LinkedIn page because those announcements are made there. In terms of the community, we also organize, hackathon, here in the city. Just a few days back, we organized a hackathon, for the high school student, and it gives me immense happiness to say that the Fredericton School was actually the winner. So this is just a bit about our strategic priorities as an institute. Now that our today's topic is with respect to datasets, I thought it would be nice to sort of give an introduction of what are different datasets available on our website. If you look at the screen, we cover the datasets from different areas and different topics within the cybersecurity domain, large language model, the dark web, the DNS datasets. If you look at the list of our speakers today, our first 2 speakers would cover datasets on IoT. Our third speaker would cover graph learning, and our last speaker would cover IIoT. So we have datasets on different topic on our website. So again, if you're inquisitive and if you're somebody who wants to keep up their knowledge base with respect to cybersecurity, I would urge you to visit our website. And with this, I think we move on to the much interesting part of today's session. These are our 4 speakers. Our first speaker would be Dr. Mahdi Rabbani. Our second speaker, Dr. Mahdi Rabbani, would be talking on a topic with respect to IoT device. Arun would also, speak with respect to a topic on IoT devices. Our third speaker would be Mr. Griffin. So Griffin is going to cover, malware analysis, and that will be followed by Erfan. Erfan is going to, cover a topic around IIoT, Industrial Internet of Things. With this, I will introduce our first speaker for the day. Our first speaker for the day is Dr. Mahdi Rabbani. Dr. Mahdi is a postdoctoral fellow at the Canadian Institute for CyberSecurity here at the University of New Brunswick. He currently leads two projects, one on detecting the smishing attacks and another on mitigating the credential tweaks attacks, while also contribute to a separate malware analysis. Previous to this, Dr. Mahdi led a project focused on access management system for IoT devices, including IoT device identification and anomaly detection. Prior to this, Dr. Mahdi was a visiting researcher at the Dalhousie University, where he focused on machine learning and deep learning approaches for detecting DDoS attacking in IoT devices. He received a full scholarship for his PhD in computer science and technology at the Nanjing University of Science and Technology in China, where he graduated in the year 2022. His PhD dissertation was titled MLDL Approaches for the Malicious Behavior Detection and Recognition in Intrusion Detection Systems, demonstrates his commitment to advancing the field. Additionally, Dr. Mahdi completed his MTech in Artificial Intelligence at the University of Mysore in India before pursuing his doctoral study. Dr. Mahdi has contributed to the field of cybersecurity with numerous publications in various journals. His research his research interest includes AI for cybersecurity, malware analysis, graph learning, machine learning, and deep learning based network anomaly detection and recognition, as well as the privacy enhancing techniques for IoT devices. This was a very short and a brief introduction to Dr. Mahdi. And at this point, I invite Dr. Mahdi onto the stage, or I should call it a virtual stage. Why don't Dr. Mahdi, why don't you please, share your video and your presentation?
Hello, everyone. And thank you very much, Sumit, for introducing me. So today I will talk about CIC IoT-DIAD 2024 dataset, which is a dual function dataset for IT device identification and anomaly detection. As Sumit introduced me, my name is Mahdi, and I'm a postdoctoral fellow at Canadian Institute for CyberSecurity. Today, I will talk about the research objectives and dataset overview, and which contains two different phases. Phase one for device identification, and I will talk about the behavioral-based features for device identification, and I will also talk about identification of the devices based on features from HTTPS and user agent. And in phase two, which is related to anomaly detection, I will explain how we detected individual attack, and then how, as a kind of individual attack detection, and how we, considering all of the attacks in one class, how we can identify, let's say, anomalies among the benign traffic. And I will also talk about a scenario where we had for zero-day attack detection. And at the end, I will talk about the integrated model that we had for both device identification and anomaly detection, and conclusion. So the first objective was IT device identification, how we can identify and classify different type of IoT devices based on behavioral patterns. And also we extracted a behavioral feature from the payload and the header of the packets. And as I mentioned, we have separate features for identifying the IT devices from the HTTPS traffic. And in anomaly detection, we have detection of individual attacks, where we have 7 type of main attack categories, and also detecting anomalies, which we can call it abnormal behaviors against benign traffic. So, and just an illustration of the objectives. So if we are talking about the IoT devices and we want to have a kind of access management system. So initially, when we want to buy something from Amazon, we are logged into our account in Amazon, and then we buy something from Amazon, and then there is a payment that conducted, and in that case, the user is actually doing the whole process. But if you want to replace it with the IoT devices, let's say if an Alexa wanna buy something from Amazon, initially it's received a comment from the user, and then the Alexa should browse Amazon website, and when everything is done and the IoT wanna pay the amount through a payment company, so the payment company should understand that what is the type of the device that is connected and wanna go for a payment, and in that case, let's say that the payment company should understand that it's Alexa and it's a smart speaker and from the Amazon, the vendor's Amazon. And then at the same time, they have to understand the behavior of the device for whether the device is under an attack or the behavior of the device is normal. So in the first phase, we will, as I mentioned, I classify the devices based on the device behavior, and we have different type of IoT devices in Canadian Institute for CyberSecurity devices, camera devices, audio devices, lighting, power outlet, and then home automation and hub devices. And so this is a workflow of the approach that I want to talk for IoT device identification. So first we collected network traffic data from different IoT devices, and then we have a process PCAP to CSV. We extracted the features specifically for identifying IoT devices, and then we have some other process for preprocessing and feature extraction, feature conversion, normalization, reduction, and selection. And then when we have a kind of significant features for identifying devices, we used a machine learning model for identifying the type of the device. So as I mentioned, it's a behavioral-based feature for identifying different type of the IoT device categories. And then here we extracted behavioral-based features. I will explain and then put them in some main categories. And we have some specific features for HTTPS and user agent. So if we want to just put them all in some main categories, we have features from network protocol, we have features from handshake and TLS. We have timing feature, and then there are some like very important features from user agent string, user agent browser, operation system, and a device. And also there are some statistical features that we generated based on the previous features that I explained. And the second phase, anomaly detection for IoT devices. So we had some features for device identification. Now we wanna come up with new features to classify the devices and also detect if the device is under an attack. So again, it's similar to the previous framework. We collected traffic from IoT devices, and then in the previous framework, we had some features extracted for classifying IoT devices. But here we need some other features that can help us to detect malicious behaviors from the benign traffic data. So for example, here we want to identify if like a camera is under an attack or a smart speaker is under attack, and how they behave when they have benign traffic, when they are their behavior is normal, or when they have some sort of malicious behavior. So and here we have 7 main attack categories: distributed denial of DDoS, and then web-based attack, recon attack, DOS attack, and then Mirai attack, and then spoofing and brute force. And for each main attack category, we have some subcategories of those attacks. And if you see in our website, we have main folders for the main attack categories, and inside every folder we have sub-attack categories for different subcategory of the attacks. So, and this is the total number of features that we extracted. The black color are mainly for device identification, and the other remaining features are for anomaly detection. So I just want to explain briefly for the feature that we extracted for anomaly detection. So we have a stream feature, and the definition is a sequence of packet exchange between a specific source and destination. And it actually represents a single communication session between 2 endpoints. And the role of these features in device identification and anomaly detection is identify specific communication session and their characteristics by analyzing stream. And if there is an unexpected spike in traffic or changes in session duration, that can actually signal a potential security incident. And here I just want to compare the actual number that we extracted from the data set. For example, here we have the average of total packet in the same stream in 30 seconds for benign traffic. And then you can see that there is a difference between when we measure it for benign traffic and then when we have it for DDoS attack and also for spoofing. So, and for channel features, the channel is the communication pathway between 2 devices, and is present the logical connection for which data is transmitted. And what is the role of this feature in identification and anomaly detection? It actually helps in mapping out the network tractions, showing which devices are communicating with each other and how frequently. And sudden increase in an unexpected communication path can indicate compromised device or unauthorized data transfer. And again, if you want to compare this feature between the benign traffic and different attack, so we can see that for benign traffic, average of total packet in the same channel for 30 seconds was 234. And we can see that for other attack categories, specifically for DDoS and then recon, it is specifically for DDoS, it's much higher, and also for recon attack. And jitter also is very important feature. It's the variability in packet arrival time. And it's measured the difference in the delay of packets as they travel through the network. And the role of this feature in identification and anomaly detection, it consists jitter pattern help to in identifying the type of traffic, and sudden increases in jitter can indicate network congestion, faulty devices, or deliberate attack aimed to disturbing the communication. And again, if we want to compare the jitter, the average sum of jitter of the same stream in 30 seconds, we can see that for for DOS attack, it is very less than benign traffic, and also for brute force, it's much higher than benign traffic. And if you want to compare three of them in terms of the numbers for benign traffic and different attack categories, of course, for one individual feature, we may not be able to have a kind of strong difference between the benign, but when we compare and when we have three of them together, then and the combination of these three features can help to identify anomalies against benign traffic. So we also extracted these features in different time period in 1 second, 5 second, 10 second, 30 second, and 60 second. So again, combining all the three features in one time may not help, but if we calculate in different time period and have all of them together and train a machine learning model for identifying anomalies or abnormal behaviors against benign traffic, it is very helpful. So the advantages of having different calculating these features in different time periods is enhancing anomaly detection and comprehensive behavior, and also resilience to noise. And there is a disadvantages because we will have more features, and definitely the data set would be larger. If we want to train a model, the training time would be higher than when we don't have for the different time. But when we have all of the features, we can go for feature extraction, feature selection to come up with some specific features for the task that we want to do for either for anomaly detection or for device identification. So, and we can see that here for 1 second, 5 second, and 30 seconds, 60 seconds, the numbers are different for benign traffic and different attack categories. And we also have some new statistical features that we extracted from the data set. So count, mean, variance, and sum. And we have calculated for all the features that we extracted. Again, we can see that count, mean, and variance, there is different between the benign traffic and different attack categories. For example, here we can see that the count is 97 for benign traffic, but for DDoS is much higher. And even for the DOS is just 2.4. And again, for the spoofing attack here is much higher than benign traffic. So this is what we have I just explained for the all the feature together, a stream for different time, and then we extracted different additional statistical feature, count, mean, and where, and then for source IP, and then for channel, and for stream jitter. So totally we extracted 132 features for both device identification and anomaly detection. And now to see the quality of the features that we extracted, so we can see that for different individual attacks against benign, we have calculated accuracy, precision, recall, and F-score, and we can see that the performance is very good for each attack. And also we combined all of the attacks in one class, and as a binary classification, we used XGBoost to and other machine learning models to detect that attack categories against benign traffic, and we can see that the XGBoost classifier performed better and then less training time compared to decision to random forest and some other machine learning models. So and we also to see the effectiveness of the feature that we extracted. It is a simple scenario for zero-day attack. So for training, we didn't consider the brute force. Trained the model based on the other attacks and then benign, and then we used brute force in testing. So of course, the result is not as good as the individual attacks, but here, since the model didn't see the patterns of that specific attack, so the performance for example, for recon attack and web-based attack was less than the others, but still it's more than 90%. So, and this is the integrated model that we had for both device identification and anomaly detection. We have a extracted feature for both phases, and then we classified IoT devices, and then we detected anomalies against the benign samples. So, and we have, of course, two labels, MAC address for device classification, and then another label for anomaly detection. So, and this is a result for both phases. So, classifying IoT devices and then detecting anomalies against the benign samples. In conclusion, what we have done, we come up with a fast and accurate model that was developed using behavioral-based feature to classify the devices with the minimal computational overhead. We extracted behavioral-based features, and we didn't consider the identity-based features. For example, MAC address, we didn't use MAC address for the identification. And these features were sufficiently effective in classifying the IoT devices. And we also consider a scenario where we have traffic for HTTPS, and those features were useful for identifying the devices. And we extracted a specific feature to identify malicious behavior within the benign traffic. The extracted feature include key characteristics such as stream, channel, and jitter calculated over multiple time period, along with various additional features. And we come up with a unified model, which was built to first identify device type and then detect anomalies, enabling a robust IT security. And thank you very much. If you have any question, I will be happy to answer.
Thank you, Dr. Mahdi, for this insightful presentation. Let me just see. It seems we have a lot of questions, but before we move on to the next speaker, I think we have time to ask you one question. So the question is, did you apply any feature selection techniques to reduce the dimensionality of the feature space?
Yeah, that's a nice question. Yes, because we have many features for anomaly detection and device identification. And of course, we don't need all of them together for specific tasks. If we want to go for device identification, we can use feature selection techniques to reduce the number of features and then use those features. And of course, we have to compare with the total feature, but we have done it. It's available in the paper that we published for this dataset.
Okay. Thank you, Dr. Mahdi. Thank you for the presentation, and thank you for also taking the question. And with this, we move on to the next speaker for the day. Our next speaker is Mr. Arun Kaniyamattam. Mr. Arun's presentations is beyond packets, unmasking IoT attacks through flow-based features. So before we move on to Arun's presentation, allow me to just give a very quick introduction. Arun is a cybersecurity software developer working here at the Canadian Institute of CyberSecurity. He holds a master's in computer science for the University of Louisiana and a BTech in biotechnology from Indian Institute of Technology, Guwahati. With over 5 years of professional experience, he's specializing in designing analytics frameworks and developing software solutions. His current research focuses on anomaly detection to combat stealthy attacks in heterogeneous IoT environments and on post-quantum cryptography for securing resource-constrained device against future quantum threats. Arun, welcome to this part of the session. So at this time, I would request you to please, share your screen, and like I said earlier, stage is all yours.
Thanks for the introduction, Sumit. So as Sumit mentioned, my presentation is on Beyond Packets, Unmasking IoT Attacks through Flow-Based Features. So my colleague, Dr. Mahdi, had already presented, discussed his an approach our team used for packet-based feature extraction process. So this is an additional approach our team explored to using flow-based features. So the outline of the presentation is going to be as follows. So first I'll share the motivation on why flow-based metrics are a good approach for such problem. Next, I will move on to the corpus that we used as the network capture files in PCAP format for the feature extraction process. Then our flow feature extraction pipeline on how we turn these PCAPs into per flow statistics. Following this, we move on to the flow-based feature set. Then we move on to the experiments we performed with the data set and the results we got. And finally, we wrap up with the research applications that we believe it can be used for and the conclusion. So for the motivation, as we all know, in the today's growing IoT environment, threats are increasingly becoming stealthy and diverse. So many adversaries exploit the fact that payloads are often encrypted and or proprietary. And then secondly, IoT deployments are currently in heterogeneous environment. So like a one-size-fits-all packet deep inspection won't scale. Then devices also face severe resource constraints. So, making large models infeasible on most live environments. And finally, there is a gap in existing datasets as few publicly available datasets capture both the benign and attack scenarios at flow granularity. So these challenges motivated us in going for this particular approach. So now moving on to the corpus that we use. So we made use of the CIC IoT 2023 dataset. This was constructed from real-world IoT devices deployed in a large-scale testbed. So the subset of these devices were compromised to execute different attacks, and these were captured in PCAP format. And then these attack categories were grouped into attacks were grouped into 7 categories based on the tactics like flooding, which contains DDoS attacks and DOS, and then probing attacks like reconnaissance, then web-based attacks, brute force, spoofing, Mirai malware, etc. And also in the same time, benign traffic was collected. In addition to the attacks collected, the dataset included extensive periods of normal traffic. So being able to capture the benign data gives the necessary contrast for anomaly detection. Now, moving on to the flow extraction process. So flow-based analysis essentially collects the essentially process the metadata that is available rather than the actual payloads, thereby delivering scalable and privacy preserving visibility into network behavior. So here you trade the the forensic depth of full payload inspection for speed and scalability here. So one record per flow rather than multiple packets. So that means you can run anomaly detection in real time across environments with a huge number of devices. So in short, what you're getting through flow-based analysis is anomaly detection of attacks at a scale, fast and efficiently with minimal privacy impact. So now let us try to define what is a flow. So a flow is essentially a group of packets transmitted between two endpoints, client and server, over a protocol. So it is essentially like a 5-tuple that includes source IP, destination IP, source port, destination port, and protocol. So you can think of it as one conversation. For example, your phone talking to a web server over HTTPS. So here you can see a Wireshark screenshot of a HTTPS interaction. So in the first step, you can see the TCP handshake happening, where you have the SYN ACK, and ACK. So these from these packets, we are able to harvest header level features like time to live, initial window size, sequence numbers, etc. Then moving on to the key exchange. So once the TCP handshake is established, then it moves on to the TLS part. So the client would issue a client hello, and the server returns a server hello. And in this, we can record the length of these packets, the list of the cipher suites, the length of extensions, and the list of extensions and signatures. Then moving on to the encrypted application data. So after these handshake, application data flows encrypted through these TLS records. So while we can't see the content, we can still capture rich statistics like the number of encrypted packets, inter-arrival times, packets per second, etc. Then when we move on to the four-way handshake, so this happens when essentially the session ends. So the four-way handshake, FIN ACK handshake closes the flow. So we can log many, like how many flags have occurred and the timing between them, etc. So in essence, we can aggregate a lot of features, which include all the type of service values, all the flags, window information, options, etc. So this is being done here using CIC Flow Meter, which is an open source tool created by CIC. So this systematically converts these raw packet capture files into bidirectional flow records. So this bidirectional flow analysis allows it to calculate statistical time-related features separately for both forward and backward direction, which provides a comprehensive understanding of the flow. So it accepts as input a directory of PCAP files, and through configurable parameters, it converts all these packets into flows that, like all the packets that share the 5-tuple, will be converted into discrete flow objects. Then, like here, you can see an HTTP session in Wireshark. So the upper panel here displays a typical Wireshark trace, which contain all the handshakes, the TLS exchanges, encrypted application data records, and the TCP four-way teardown. Now, each line here corresponds to a single packet event with the full header and payload details. Now, then here we are highlighting all the packet events that will belong to one flow. So CIC Flow Meter, it will collapse these dozens of lines into a single flow record, thereby reducing the data dimensionality. Then following this aggregation, each flow will be represented as a fixed feature length vector. So here you can see a flow ID column and subsequent columns from F1 to F76, which will contain quantitative metrics about the flow. Then finally, CIC Flow Meter will exploit these flow records into CSV files, which can be inspected in a spreadsheet or ingested into data science toolkits. So here you can see real flow entities with fields for forward and backward packets, then byte totals, flow duration, and other statistics. So now let us try to place the flow extraction within our comprehensive pre-processing flow. So first, PCAP files were processed by CIC Flow Meter to generate these flow records. Then our feature extraction scripts compute a total of more than 80 statistical features per flow. So these descriptors then undergo pre-processing and data cleansing, and etc., to produce a streamlined feature set. So these resulting CSV tables constitute the input to machine learning models that can be used for the anomaly attack detection problem. So now let us just move on to the actual dataset features. So so every flow record will have over 80 statistical features. These would include basic flow identifiers like the phi tuple. Then another important set of features are the inter-arrival time features. So these are based on time intervals between sequential packets within a network flow. So these are the set of inter-arrival time features. So there are three types of inter-arrival time features here. One is the inter-arrival times between two packets sent in the flow. Then you have inter-arrival time features for two packets sent in the forward direction and two packets sent in the backward direction. So these features are important because this helps you understand various time delays that might be happening between packets in a network session, which can be indicative of certain abnormalities. Then moving on to the next set of features. So these include flag features. So they basically calculate, measure the existence and frequency of specific TCP flags in the packets. So there are two kinds. So sort of calculate the number of PSH flags sent in the forward and backward direction, then the urgent flag that are being sent in the forward and backward direction, and then certain other flag counts here. So by monitoring the frequency of such flags, it is possible to distinguish between normal and abnormal terminations or some kind of SYN flood attacks, etc. Then moving on to the next set of features, those are active idle features. So here we collect features from both active and idle TCP flows. So these are the main features that are involved here. So in this, active means something which can be helped in identifying abnormally idle or active duration, where then even active max can be used to identify good insights about the upper limit of flow activities, and as a result maybe detect anomalies based on longer connections. Then moving on to segment, bulk, and byte. So these features sort of provide insights about the size of the data flows. So these can be grouped into four, which are segment size averages for forward and backward direction, then bytes per bulk average in forward and backward direction, then packet per bulk in forward and backward direction, and finally for bulk rate average in forward and backward direction. And moving on to the final set of features, those are other statistical features which sort of give you information about the flow. And so to be final, these are the set of 84 features that we generated using this process. And and now let us move on to the experiments we performed with this feature dataset. So the dataset had about 2.3 million flows, which included both benign traffic and 7 kinds of attacks. So we framed 2 detection tasks here, both a binary anomaly detection of attacks. So the first kind was a benign, trying to classify a benign flow against any kind of attack. And the second kind was where only one kind of attack was used against benign to be detected. So we, to benchmark, we trained 5 off-the-shelf classifiers like XCG-Boost, Decision Tree, Random Forest, Multi-Layer Perceptron, and Logistic Regression. Then we also tried to apply RFE, Recursive Feature Elimination, to retain the top 40 most informative features to see how it performs in a more streamlined approach. And also additionally to evaluate, we utilize standard metrics like accuracy, precision, recall, and F1 score. Now, this is the results that we got against in the first set of experiments against all attacks. So you can see here that XCG Boost is the best performing classifier with about 95.92% accuracy using all the features available, and 95.85% with just the 40 features, while cutting the test time from around 6 seconds to under 3 seconds. Random forest is also nearly identical, but the training time is a lot larger. So the key takeaway here is that our flow-based feature representation enables a high accuracy across millions of encrypted flows, and also that recursive feature elimination, the feature selection process we used halves the feature set with negligible loss, making real-time edge deployment practical. Then using XCG Boost, we also perform the per attack classification. So here, for each threat, we trained on both the full set of features and also the 40 features selected by RFE. So notice that across every attack, pruning to 40 features barely changes accuracy or F1. Like brute force stays at 99.6% accuracy, and DOS and Mirai remain about 99.8%. While at the same time, while using RFE, the test times are shrinking by roughly half. So this demonstrates that a carefully chosen subset of flow-based metrics will deliver the same detection power as the full set while cutting the computational cost, which can again be crucial for real-time or edge-level deployment. Now, moving on to the conclusion. So we essentially leverage the existing flow data, like the data set available with CIC IoT. And by focusing on flow-based features, we were able to condense the IoT traffic into a compact set of actionable data. And then also trimming to the top 40 features by using RFE, we are able to maintain peak detection accuracy while slashing the computation costs. So this sort of validates that flow aggregation is a powerful privacy-preserving approach for IoT anomaly attack detection. Now on to the future direction. So as we look ahead, there are several promising avenues to extend this flow-based approach. First, we can explore more sophisticated modeling techniques that capture relationship across devices and flows, which can help in uncovering patterns that flat feature vectors may miss. Second, adding explainability layers would triggered and helps in speeding incident response. Third, we also aim to push our detection models down to edge so that we can score flows in real time on IoT with minimal overhead. And finally, constructing temporal flow graphs and applying graph embedding techniques may reveal more slow burn threats that evade these snapshot-based detectors. So together, these directions will make flow-based IoT security more accurate and practical for real-world deployment. So thank you for taking the time to hear the talk. And maybe Sumit, if there are any questions, I would be able to answer it now.
Thanks for that, Arun. That was a nice continuation to what Mahdi started with the discussion on this particular data set. So thanks for your presentation. Let me just see if we have any question. We certainly do have some. So just a minute. The first question is, why emphasize the anomaly detection flow-based feature sublet for anomaly detection rather than the pocket level feature?
Oh, thanks for the question. So yeah, it essentially comes down to efficiency and practicality. So sometimes, it might be difficult to inspect per packet payload across a lot of devices. So flow-based aggregation here would allow you to collapse a lot of packets into one metadata record per conversation. So this would essentially cut the data volume by orders of magnitude, which makes it feasible to run on resource-constrained or edge devices in real time. Plus, also flow features mostly rely only on headers, timings, and flags, etc. So there is no need for decryption. And packet level features, in contrast, may sometimes require deep inspection, which doesn't always work on streams, or sometimes might not scale on an IoT network.
Thanks, Arun, for this for this explanation. We do have a lot of questions, but we just don't have the time to take all those. So unfortunately, with this, we'll move on to the next speaker. And before we do, thanks, Arun, for your questions and for your insightful, presentation as well. Our next speaker would be Griffin Higgins. So Griffin is his topic is CIC statically generated graphs for malware analysis. Griffin Higgins is a PhD student in computer science at the University of New Brunswick and the cybersecurity software developer at the Canadian Institute for CyberSecurity. He completed his Bachelor's of Science, Bachelor's of Arts in Sociology, and Master's of Applied Cybersecurity, plus research intensive cyber knowledge studies from UNB in the year 2020, 2021, and 2022, respectively. His research interests include the cyber threat intelligence and the privacy-preserving deep learning and adversarial machine learning. Although it's not a part of his introduction, but I must mention the hackathon that I mentioned. Griffin is the person responsible, behind the hackathon that we organize for high school students every year. With this, I welcome, Griffin to this segment. Griffin, like I said to the previous speakers, the stage is all yours.
Awesome. Thank you so much for the warm introduction, Sumit. And yeah, we always love putting on hackathons and different events for students. So I hope everyone can see my screen and hear me well. Just give me a little shout if not. But yeah, so today we're going to be talking about CIC statically generated graphs for malware analysis. It's May 9th, so let's jump into it. As Sumit mentioned, I'm a PhD student in computer science here at UNB. I'm also a cybersecurity software developer here at CIC, and I have a background in computer science, sociology, and cybersecurity as well. So on the agenda, we just did the introduction, and after this, we're going to look at some background. There's a lot of different pieces to put together to understand what this data set is. It's quite a unique data set. So today, instead of focusing on like the nitty-gritty features and stuff, I just want everybody to come away understanding what this is and how it can be applied almost at like an undergraduate level, if that's kind of the minimum bar. After that, we'll cover the data set and answer a lot of questions about it. And then finally, we'll take some Q&A at the end. And I'm also going to start my timer. Perfect. So I'm going to hit you with this right up front. I always like to start with a bit of a bang because this is actually what we're going to be moving towards understanding. And as you may have guessed, it is kind of scary looking, and it's because it's malware. And in this case, it's an explained piece of malware as a graph. We're going to talk a little bit about what that is, but just to give you like a precursor idea before we get there. So, but first, before we talk about this, we need to talk about a couple other things. And principally, what should you know before you start to dive into this data set? So we're going to cover a little bit about malware, a little bit about malware detection, static analysis, graphs, program graphs, and then graph learning, and how they all relate to our data set. We're just going to talk pretty plainly about them right now, just so that people can get an idea about what this data set is. So in terms of malware, what is malware? They're programs designed or misused with specific malicious intent to cause harm to other people or otherwise violate CIA. And there's various different kinds of malware families. We might know some of the more common ones like ransomware, worms, etc. So that's a little bit on malware. In terms of malware detection, very simply, I give you a binary program or a program, and you tell me if it's malicious or benign. So that's pretty simple, but there is a little bit of a bonus in terms of if you do make this kind of prediction, can you also tell me what parts of this program lead you to believe that prediction strongly? So that's kind of another part. After this, we're going to talk a little bit about static analysis. So again, just very quick fire things. I give you a binary program and I want you to tell me what it does, but the catch is that you can't actually execute it. You can only really look at the code and try and make guesses about it that way. In contrast to something we might say is dynamic analysis, where we actually run the program in order to talk about it. Another thing we're going to talk about a lot today are graphs. So this is kind of a strange word for some people if you're not in computer science, but it's the same thing as what most people would know otherwise as a network. And networks are just a data structure, and they have a set of nodes that are sometimes called vertices, as well as edges. And these edges between nodes, the things that connect them, they can be directed, i.e. like you can go from A to B, but you can't go from B to A, or they can be undirected in that like you can go from A to B or B to A if you have two nodes. There's many different kinds of graphs. Some of them are called multi-graphs, where you might have multiple edges between the same two nodes. And graphs can also have attributes. So we might talk about the graph as a whole. It might be malicious or benign. We might also talk about a node, and we might look inside of it and talk about its instructions, right? Or we might look at an edge, and we might assign it a value in terms of how much it contributes to a final prediction of something being malicious or benign. So these are all just kind of things related to graphs that we might extend to programs later. And this is a good segue because the next part is on program graphs. And essentially here, I give you a binary program, and I want you to transform it into some kind of graph. And typically there's two ways to do this. One is through control flow graphs, where essentially we take sequences of non-branching assembly instructions and we stick them into one node. And then whenever the code branches off, we create an edge to that other node and then have all of its assembly instructions. And we keep going until we've exhausted the whole program. Similarly, we can also consider function call graphs. Except in this case, we're not considering sequences of non-branching instructions. We're just considering the functions that you and I might classically know if we're doing some programming. So, okay, this is a little bit more on program graphs. We're kind of chugging along all these different pieces of our data set. What else are we going to talk about? One of these things is going to be graph learning. I know some of my colleagues have and are going to be talking about this a little bit more. But in our work, we apply deep learning techniques to graphs via graph neural networks. And the reason that we do this is so that we can start to talk about the behavior of malicious programs rather than just matching signatures. And if anyone wants to ask me a really good question at the end, ask me like what the benefit of doing this would be. So I wanted to also include this short little video just talking about graph learning. And here we start off with this network and all these nodes. We might recognize them as people. And essentially, we're going to give each node a message. And what we're going to do is we're going to share that message with all of our neighbors. And then after we're done, we're going to take that message and then we're going to start sharing it out with our message again. And we're going to do this over and over and over and over again. So we might ask, what is the purpose of doing this? The purpose of doing this is so that we can start to talk about each node and its little neighborhood around each node. And then hopefully after we do this kind of message passing enough times, maybe even millions of times, we can get a good representation for what the graph actually is at a structural level. And we will be able to represent that with a sequence of numbers that are typically called an embedding. And we're going to use this embedding to make predictions about whether or not our graphs are actually going to be malicious or benign. So that's just a very crash course thing in graph learning, just so that we can get a very rough idea. There's a lot more to it, but again, just getting a rough idea for what this data set could be used for and the different parts of it. So again, there are different kinds of tasks in graph learning. The one we're obviously most concerned with in our work is the graph level tasks. So if I give you a program, can you tell me if it's malicious or benign? But there are other kinds of tasks. We might talk about node level tasks that are kind of in orange here. So predicting what kind of class a given node might be. We can also talk about edge level tasks. So predicting if an edge exists or if there's a certain kind of value on an edge. It can extend far beyond just graphs and graph classification itself. So, okay, great. We've covered all of the very high level things related to our data set. And now we're ready to jump into some of the details about it. So first question you might have is why make this and how did this come about? So we previously were working on an industry project and we still are. And it focused on graph learning and using graph learning for malware detection, unsurprisingly. So in this work, explainable malware detection through integrated graph reduction and learning techniques together with my colleagues, we basically set out on this task and we found something very interesting. And that was that the graphs that we made from these programs, these control flow graphs and these function call graphs, tended to be quite large. And so the majority of our work was spent trying to figure out how do we actually reduce or collapse the size of these graphs. So that's why it's talking a lot about graph reduction. But apart from this, we did all this work and we looked at the various stages of this pipeline. And we thought, okay, let's actually make this available for other researchers so they don't have to set up this big pipeline or get all these malware samples and convert them to graphs and do all this hard work. Let's just give it to them so that they can get to work. So that's the why, but this is the how. So I was always thinking earlier about the old Discovery Channel, how it's made. We're going to start from the very beginning and then go all the way down to how we actually get explanations from the graphs. So starting out, we obviously need some malicious binaries. If we remember earlier, this task of if something is malicious or not, we need a binary to start with. So in our work, we consider 3 different data sets. We consider the DIAD dataset, the PE for machine learning malware detection dataset, as well as the BODMAS dataset. And some of these datasets are open, so you can just go download them yourself, and they contain both malicious and benign samples. And some of them are closed, so you basically have to request access, and then they might actually give you the binaries. Also in our work, we're just considering only PE files, and essentially we're focusing on the x86 architecture. So after this initial stage of getting all these data sets and kind of filtering them down a little bit to get exact samples that we want, we can begin to move forward with actually creating the graphs from these binary samples. So we do that in many ways. This is also a good question if someone wants to ask it later about the challenges that exist here. But again, I want to be in time, so I'm going to skip it. So we take these binary samples and we can pass them through various tools, one of which is called Anger. And this is the thing that will actually generate our control flow graphs and function call graphs for us. And it will give them back to us as a network X object. And one of the really interesting things I think about this data set is that this can be helpful for both malware analysts and graph learning specialists. So if you're really focusing on malware analysis, you can use these graphs because they are the things that are actually going to contain the raw features. So if you go and you open up one of the graphs and you go and you open up one of the nodes, there's like a small treasure trove of information in there. We couldn't even explore all of it, but it's there for researchers if they want to. Another important point is that these graphs here are not actually used for training or testing. They are just attribute graphs that we actually use to make the next segment, which are going to be called the embedding graphs. So after we have these attribute graphs, the thing I just talked about, we're going to make the embedding graphs, and we're going to take all of these nodes and the node features. So basically, when we think to the video earlier, how each person in this network had some information above them, like that little message, that's actually just a list of numbers. And what we're going to do is we're going to use this to actually pass the messages around. But before we begin, we actually have to make this message. So we look at all the feature nodes for each node to make that list of numbers. A little rambly, but I hope that got through. After this, we can take it and give it to another program called PyTorch Geometric. And these are actually the graphs that we will use for training and testing all of our various graph learning models. And importantly here, these are the graphs that you're going to really care about if you're into graph learning, or maybe if you're trying to merge these two fields of malware detection and graph learning. So they have all the embeddings for each node, as well as the positions of like where they occur, because maybe you want to prune off some of the nodes, but also have references back to where they were in the original graph. So that's a little bit more about the different stages of this pipeline. And as we keep going through, we can start to look at the graph pruning algorithms. So we don't include these samples in our data set, but they're free if anyone wants to apply the same algorithms, they're welcome to do so. And then at the very end, we might actually try and think about the explanations for these graphs. So after we pass them through our different models and predictions are made about them, what are the nodes, if we recall back to the malware detection part, it was that kind of that bonus. What are the nodes or the edges that actually contribute to a given prediction? And can those be used in the future? So again, after we have all of the data set, we're kind of working through how this is made. We can take a look at the different machine learning models or graph learning models, and we can do inference on them after they're trained, so we can answer those initial questions related to malware detection. We can also look at the explanation, the thing we just talked about. So that's where it all kind of fits into this little ecosystem that our data set is extracted from. So you might also ask, what's actually in CIC? Like if I go and I download it right now, what is actually there? So we give you the following things. We give you the attribute graphs that we talked about. We give you the embedding graphs that we talked about. And then we also give you the explained graphs. So if you take the same sample for each one of these, it will have the same structure. Like if you looked at a plot of it or you just visualized it, it would be the exact same. But the features, the information in each of these is going to be slightly different. So, okay, you might actually also ask, what do these look like? We've been talking about these at a very abstract level for a little while. So these are two images of the function call graphs where we use the function name embedding technique, where we just take the name of a given function and we pass it through a sentence transformer, which gives us basically a list of numbers that we place over the node, very simply put. But here we can see the malicious is going to be on the left in red here, and then the benign sample is going to be on the right in blue. So we can kind of see that these look like quite dense graphs, but actually it gets much worse. Because once we go to the control flow graphs where we use the assembly embedding technique, we can see that the size of these graphs just explodes. So in the malicious case, there were a few samples, I think, that reached almost to 300,000 nodes each. And once you start to do anything at that level, your life becomes difficult. Even to generate the images you see now here, it took, I would say, like 8 to 12 hours for it to actually arrange the plotting coordinates for each one and then actually to render it. So you can imagine now why the graph reduction techniques would be important if you're going to do something like graph learning. So yeah, that's just a couple images of the graphs themselves. Very cool. And one of the last things we're going to talk about is where actually is CIC statically generated graphs 2024. So if you go to the Canadian Institute for CyberSecurity website, and this is the same for all of my colleagues that are here talking today, if you go to the datasets tab and then you kind of scroll down, you'll be brought right to all of our datasets. Eventually, if you click on one of them, you'll be brought to like the dataset description page. And then finally, if you scroll all the way down to the bottom, you'll see a little place to actually go and download. When you click that download button, you're actually going to be brought to like the server where all the data is hosted. And for our data set, you're going to see the following, where we're going to have essentially those 3 directories we talked about, which contain the attribute graphs. They're in the CFGs, FCGs, a little bit of a tongue twister, as well as the embedding graphs, and then finally the explained graphs. We also include like a zipped version of the data set because some, especially the embedding graphs, are quite large. They can reach almost 230 gigs. So one of the things we do is we make each and every one of the individual samples also available to download if you so choose, because maybe people don't have a couple hundred gigs just sitting around on their disk and they'd rather just have a couple samples. So yeah, that's a couple of our references for obviously the BODMAS dataset, the DIKE dataset, and the PE for machine learning dataset. Thank you to all those people for the hard work in collecting those samples that enabled us to make the graphs in the first place, as well as thank you to all my colleagues for their hard work on our papers. So yeah, with that, I think we've covered the following things. What should you know to understand the CIC dataset? Why make the dataset? How is it made? What's actually in it, and where can I get it? So with that, I think we're wrapping up a little bit early, but maybe we can take a couple more questions if that's the case. Thank you so much.
Thanks, Griffin. That was I mean, certainly insightful, and it's always nice to show our viewers how they can access some of those data sets.
Yeah.
Let me just see if there are questions that
Sure.
you have in the chat section. It certainly seems we do have a few, so I'll go about and read the first one. So, what is the largest challenge related to using the static CFGs and FCGs?
Yeah, no, that's a wonderful question. So I think just the sheer size of these graphs, it can sometimes take upwards of hours or even days to get through a whole data set if it's unpruned, right? And another challenge is whenever you're working with graphs, sometimes you should get a little scared because the one of the things that we're obviously concerned about in computer science is this notion of computational complexity, which just describes like how hard are the problems we face. And whenever we start talking about graphs, especially large graphs, you'll kind of see computer scientists start to sweat a little bit. So any way that we can to reduce the size of those graphs makes our life, in some cases, exponentially easier. So that's the main challenge, is just figuring out not only those algorithms, but what are fast pruning algorithms, what are efficient pruning algorithms, what are fast pruning algorithms. So that's a big one. And I would also suggest something we didn't know at the start of the project. We worked a lot with NetworkX. But towards the end of the project, one of my colleagues suggested a really good library. It's called iGraph in Python. It's really, really fast. So that would be my advice to anyone that might be taking a long time to run your programs, is try that library out.
Okay. Thanks, Griffin. That was again very insightful for people who are looking to further their research in this area. With this, we move on to the next question. What else could researchers do with CIC SGG 2024?
Yeah, absolutely. So we kind of focused a lot on the graph classification, but again, there's so much more to it. You could take a look at each one of those sub data sets, if you will, separately, even though they reference the same graphs, because you can look at the explanations for given predictions and see like what's going on with them in a little more depth. You could also take a look at the attributes. We didn't have time to look at all of them. There's tons and tons of features if people wanted to figure out how to make better graph embeddings for the nodes. That's obviously a really good direction. You can take a look more at trying out different models for graph learning, seeing if you can get better predictions, better accuracy. All those things are always great. And then the last thing would be maybe considering different kinds of tasks. So we were again focused on the graph level task, but maybe we can take a look at edge level tasks for predicting if there are going to be certain edges between nodes or not. Another interesting thing that we didn't get to was in the graphs, the positions of the graphs are given there, so you'll know which nodes might occur before other ones. So maybe you can also consider like the state transitions as a function of time, or the temporal nature, or temporal graph learning, I believe is what it's called, where you can see and make predictions about the graph as it evolves over time. So that might be like a fourth dimension to the graphs that people can maybe consider. Yeah, awesome question.
Interesting. Thanks, Griffin, for this. And the next question is kind of interesting one. Like your data sets, what is the industrial application of that?
Yeah, so obviously for malware detection, one of the drawbacks is that sometimes it can be a little bit slow because you're having to compete with signature-based detections, which are usually quite fast. But the drawback is that when we're looking at signatures or indicators of compromise, one of the big drawbacks is that they can be easily changed, right? Like if you have a hash of some kind of binary sample, which is just like its fingerprint or its signature, you might be able to change like just one bit, and then you'll have an entirely different signature that might be able to evade some kind of a detection, right? But even though that's fast, that's a big flaw that we address through graph learning, right? Because at that point, you can actually start to talk about the behavior of the program or what exactly it's doing that makes it malicious, as opposed to, okay, I just have some hash in a database, match, go about my life. Even though that's a very good approach, it doesn't get all the way there.
Interesting. Thanks for elaborating that, Griffin. Our next question is with respect to the function name embedding. So can you talk a bit more about the function name embedding and assembly embedding techniques?
Yeah, no, so that's a really good question. For the function call graphs, we can only apply the function name embedding, obviously, because they're the only ones with functions that have names. But again, we take those names and we can pass them through sentence transformers that, again, all we're looking for is just some representation for each node to have a list of numbers so that we can pass all those messages around with our neighbors and get representation for the graph. That's kind of the main purpose. But you asked another really good question, which is on the assembly embedding. So this one's a little more in-depth and intricate. So in this case, where we're considering a control flow graph, each node, again, represents a sequence of non-branching instructions. They're also known as a basic block. And what we do in this case for this particular graph is we take each and every instruction in that node, in that sequence, and we embed that instruction. And at the very end, we sum them all together. So we'll actually have a representation for the instructions within each basic block that we then use as that message that we kind of pass around. So yeah, there's a little more technical detail to it, but at a high level, that's kind of what's going on for both of those embedding techniques.
Oh, interesting. Griffins, I think, let me just quickly scan through our chat section if there are any further questions.
Yeah, sure.
I think with this we come to the end of the Q&A session with you, which means thank you for your presentation, Griffins, and thank you for answering some of those questions. They, I think, certainly cleared a few doubts.
Yeah.
And with this, we move on to the next speaker of the day. Our next speaker is Erfan. Erfan Ghiasvand, and Erfan's topic is CIC APT-IIoT, a provenance-based APT attack datasets for IIoT environment. Erfan holds a master's degree in computer science from the University of New Brunswick, where his research focuses on detecting advanced persistent threat APTs in industrial IoT systems through the provenance data analysis. He's now working as a cybersecurity software developer at the Canadian Institute for CyberSecurity. As a research assistant at the Institute, he collaborated with the National Research Council on advancing IoT security using artificial intelligence. His thesis introduced CIC APT IIoT datasets and developed a self-supervised learning framework for APT detection. Erfan's expertise lies in AI, cybersecurity, and industrial IoT security. Erfan, at this point, I would say the stage is all yours. Please share your presentation, and we're looking forward to see your slides.
Thank you very much, Samit. Thanks for your introduction. So hello, everyone. I'm Erfan Ghiasvand, and today I'm going to talk about CIC APT-IIoT, that is a provenance-based APT attack dataset for IIoT environment. So this is the outline of my presentation. I first go through a short and brief introduction, and then we are going to go through a little bit of background on what is IIoT, what is advanced persistent threats or APTs, and what is provenance data. And then we are going to go through like the generation process of our dataset, CIC APT-IIoT dataset, how we developed the testbed, what we use as the attack emulation plan, and how did we collect it and label the data. And finally, we're going to go through like a simple example of how you can actually use our dataset, CIC APT-IIoT dataset. So first of all, let's begin with the very simple question, and that is why data matters. So until now, you heard from 3 of my colleagues that we're talking about their respective data sets. So we know that the data and having a good data set actually really matters, especially in the field of cybersecurity. So the need for that is that we're trying to develop effective intrusion detection system or IDSs that we can have them, and we can have them to efficiently face the threats and the challenges that is out there for the safety or cyber systems. So to develop those efficient and good IDSs and solutions, we need to have a very good data set that have like a representation of our system and how they work. We need to have the benign samples and malicious samples in order to be able to train and evaluate our models, our machine learning or deep learning models, and with that we can develop very good solutions. So in that field, we do have lack of some realistic data set in the field of, especially for the industrial IoT or IIoT. And another thing is that those data sets that are available are usually fail to reflect the complexity of modern APTs. So the purpose of our dataset, CIC APT-IIoT dataset, is to have a dataset in an industrial IoT environment in IIoT settings. We have a combination of simulated and physical IoT devices, networks, and scenarios. We do have like a simulation of an actual real-world APT threat is that we try to have as similar as possible a scenario to a real-world APT. And our data set comprised of network data and provenance logs. I will talk about these things later, but we need to have these resources in order to be able to develop a very good machine learning solution for our first challenge. And there are various challenges in creating the data set. One of them was how to capture data, how to simulate the real world condition, and finally, how to ensure that our data has a good quality. So, to go to a little bit of background, well, first of all, what is IoT or Industrial Internet of Things that I'm talking about? So basically, you can call an interconnected network of sensors, instruments, and other devices that are networked together, and they have an industrial application. So we call this network an IoT or Industrial IoT. So these applications can be different things. For example, they can be used for manufacturing. They can be used for like energy management, and they can be used for transportation and logistics. The thing is, when you're using this kind of technology, industrial IoT, you can improve your efficiency. You can have automation in your work in industrial application. And basically, you're collecting a lot of data using the different sensors and different devices. So you can have data-driven decisions. And in that way, you can improve the efficiency of all of your operations. So, but the thing is, using and integrating industrial IoT comes with the various challenges. One of the challenges is that how to maintain the privacy of data that we are collecting. The other one is how to have the scalability for the industrial IoTs. And the most important challenge for us here is the security concerns. So why we do have security concerns for industrial IoT settings? The thing is, as I talked about this, as I provided some examples of industrial IoT, these things, industrial IoTs are very attractive targets for cyber attackers. Why is that? It's because they are basically always integrated into very critical infrastructures, for example, for power plants or nuclear plants. So basically, as they are integrated into critical infrastructure, attacking them and damaging them actually has high impacts overall. So some of the examples of such attacks that are called APTs are, for example, the Stuxnet and also attacks on Ukrainian power grids. So I talked about APTs or advanced persistent threats. So let's go a little bit of background on what is APT. So basically, we call it a kind of attack or kind of threat that is stealthy. And the important feature of APTs is that they try to remain undetected for an extended period of time and try to gain access, unauthorized access to the victim computer or the victim network. So we call them advanced because they usually have a full spectrum of intelligence gathering and the different type of tagging techniques under their hand. And also they are usually state sponsored. We call them persistence because they are not like DDoS attacks, that they are opportunistically seeking information and they're attacking their target over and over. But they are very specific. They have very specific objectives, and they try to maintain a low and slow approach. That's a very important thing about APTs. They are not constantly attacking their targets. They try to maintain long-term access and long-term unauthorized access to the target. So on that, the different resources report the dwell time, that is the average time that an APT campaign goes undetected. They usually report this dwell time between 70 to more than 200 days. So different researchers have different models of APTs. Basically, what happens, it has like different phases for each of the APT campaigns. So, for example, one of them is that it starts with an initial compromise of the network. Then the attackers or those that are behind these APT campaigns try to establish a foothold in the victim network or victim computer, and then they try to escalate their privileges and to have access on other resources or other devices. Then they try to have internal reconnaissance on the victim network. Then they have lateral movement, try to gain access to other devices or other networks within the general network. And after they reach the target, they try to maintain presence on the victim device, victim network. And finally, they complete their mission, whatever it is. For example, sometimes it's to exfiltrate some data, or sometimes it's to disrupt the operation of some industrial application. So another thing that we should know about before going to the dataset is the provenance data. So basically, provenance means any information or any metadata that describes the production process of an end product. That can be anything. That end product can be anything. But here, the end product is system resources, for example, files or processes or things like that. So there is a widely accepted form to represent and to show the provenance data. It's called directed acyclic graphs or DAGs. And here you can see the W3C prov data model that is a widely accepted form of showing the provenance graphs or provenance data. There are two core concepts for provenance graph. They're called types or nodes and relation or edges. So the important thing about the provenance data that makes it very useful for our applications is that nodes here are connected based on causality relationship and not time. So what that means is that when you have a node connected to another node, it's not because that thing happened exactly after the first one. That means that these two have some type of causality relationship between them. And because of that, and as I told you in the last slide, as APTs happen in a long time, it's not going to be like a second after another. So this thing actually is very effective for detecting APTs. So this one is like a sample of a provenance graph, how it actually looks like. It's for a 3-hour experiment. You can see we do have a lot of nodes here. Blue nodes represent the benign activities of our network, our testbed, and the red nodes show malicious behaviors. I will talk about how we can label the nodes of the provenance graph to benign and malicious in the later slides. So here is the motivations and motivations that we have for this research, and also the research questions that we try to give answer to. So as I talked about it in the introduction, we do have a lack of comprehensive data set, especially when we are trying to study the APTs and the complexity of APTs in industrial IoTs. The other thing is that as industrial IoT is growing and we are integrating them into more and more industrial application, the threat of APTs and those type of attacks are escalating, and we're trying to have some efficient solution to help to develop an efficient solution to face this kind of threats, face these APTs. And the research question that we have is to how we can develop a comprehensive APT dataset that actually includes essential information we need to be able to somehow face APTs and face the attacks that are going to happen in IIoT setting. The other one is to how we can use provenance data to efficiently utilize those data in order to improve the detection of APTs. And finally, what are the methods that we can use to use the provenance data in order to detect and improve the detection of APTs? So let's go to the generation process of CIC IoT-DIAD dataset. So first one, this is an overview of our testbed. We can see our key components here. So basically, we do have a number of virtual components and a number of physical components. You can see that we do have a host machine that hosts all of the virtual machines that are used in this testbed. We do have two benign or victim virtual machines, VM number 1 and VM number 2, and we do have two attacker VMs that are attacking VM 1 and attacking VM number 2. So VM1 is the main component here. It is basically our edge gateway, and it hosts our Caldera client, and it hosts our local and works as a local SCADA and also management device, and also it is our MQTT subscriber. It is also connected to the internet through a network interface, and basically all of the other devices have access to the internet using this one. The other one is virtual machine number 2, that is our MQTT publisher, and it works as a host of SCADA. We do have two attacking virtual machines. One of them is going to be as like an internal attacker, the other one external attacker. And we do have a couple of physical components as well. We do have two Raspberry Pis. One of them works as a PLC and sends related packets. The other one works as a access point for a wireless access point for the sensors that we have. We have a camera, we have a flood sensor, we have a couple of other sensors, and we are also able to have like on-site supervision using mobile phones, and these mobile phones are connected to these Raspberry Pi. The important thing here is that we are connected, all of these components are connected together using a network simulator. We use NS3 for that. So basically all of these components, physical or virtual, are connected together using network simulator. So this is another overview of the testbed. You can see like a high-level overview of testbed, how these things are connected. As I said, VM number 1, Ubuntu, is an Ubuntu machine that actually works as a network gateway for us. And we do have 2 Raspberry Pis, another Ubuntu, and also a attacking virtual machine from inside and outside. So for the emulate attacks that we had in our settings and we collected data on, is that we had an attack emulation plan for APT29. So APT29 is a real-world APT group that actually has a lot of attacks throughout the history. So they're a very important APT threat actor, and basically because of that, my threat attack framework has its own emulation plan for the APT29's attacks. So we use that emulation plan, and we use a number of MITRE attack frameworks, TTPs, and we use the MITRE Caldera on Kali number 1, and also on our virtual machine number 1 to perform these attacks based on what we thought about APT29. So the emulation plan that we executed contained initial access, reconnaissance, gaining access, lateral movement, persistence, and finally data exfiltration. So this is the process of collecting and labeling the data. So we basically collected 2 types of data. We collected network data and collected system host logs. So for the network logs, my colleagues talked about how we can use network logs to detect different types of attacks. So I'm not going to go through that in detail. But just can say that we collect the packets with real-time stamps, and we are also collecting host logs. So these host logs are fed into a tool called SPADE, and that SPADE gives us a provenance graph. So another thing that we have here is the reports of the Caldera that we use to perform the attacks. This report provides us with the attacks metadata and also the process ID of the malicious processes that actually caused the attacks. So using these 2 resources, we actually can label the data, label the network side of the data, and label the provenance side of the data. So after all of those, we do have a combination of provenance data and the network data that are cleaned and labeled and are there for use as a labeled data set. This is an overview of how this actually looks like, how our data set looks like. So we did had our experiment in 2 phases. In fact, the first phase was a 4-day benign activities, just benign. We didn't do any type of attack in this phase. And the next one was a 3-day attack. So we did have a lot of benign packets and benign nodes, provenance nodes, but we also had a lot of attacks that were happening during that phase. So if you can see here that we did have about 46,000 nodes provenance graph for the benign phase and about 53,000 node provenance graph for the phase 2 that is benign. But for the attacks, in total we had about more than 300 attack nodes for the phase 2. That is the sum of all of the other steps that happened during the experiment and during the emulation plan of the attack. These are some of the features that were extracted from the provenance data and provenance graph. So one of the features, for example, is ID. That is basically all of the nodes have those things, and there is the identifier for nodes. We do have types because we do have a lot of different types of edges or nodes in the provenance graph. We do have a from and to features that are specific for the edges, and they are basically the IDs for the source node and the destination node, and so on. We do have a lot of features that are useful for developing the detection tools. And this is actually how it actually looks like a provenance graph. So here you can see we do have different type of nodes and different type of edges. For example, these are processes, this is an artifact, and these edges are different type of edges that you can see, and that they're generated with different color to show the difference. And this is how actually the complete provenance graph looks like. As I said, it's just for the attack phase 2. So this is basically like a 53,000 node graph, and the blue nodes are actually benign ones, and the reds or with the other colors are those that are attacks. And to compare our dataset with the other dataset available in the literature, you can see that the thing about our dataset is that it is generated on the IoT and IIoT setting. It contains network lock and it contains provenance or host locks. So we do also have different phases of an APT. We do have established foothold, collection, data exfiltration, CNC or command and control, persistence, discovery, credential access, lateral movement, and defensivation. So just going to go through a little bit of like how we can use our dataset, how we can use the CIC APT IoT dataset. So as there are a lot of dataset out there that are focusing on the network packets, I'm just going to provide an example on how to use the provenance graph part of the dataset. So as any other data set that you are going to use for machine learning or deep learning tasks, you have to kill in the data first, and you have to separate the nodes and edges, because we do have 6 different node types and 4 different edge types. And we do have to like encode some of the features. For example, we do have a feature in the provenance graph that is pass, called pass. It's a pass of the file or pass of the directory. Whatever it is, you can encode those things, and you can encode the features. For example, I provided some examples of 3 features here. And then we're gonna have a graph something like this one. So this is like a simple example of how a provenance graph can look like. We do have different type of nodes and different type of edges. So in order to be able to fit that things, so basically Griffin somehow talked about this, we need to have an embeddings for each of the node in the graphs in order to be able to fit those embeddings into like a downstream machine learning or deep learning task. So for that, and as basically like a baseline method and baseline solution, we use node to wake approach. It works based on a word to wake technique, and it does some random walks on the graph, and it's actually works as counts the graph as somehow a homogeneous graph. So it's not a very good technique for the provenance graph, but as I said, it's mostly like a baseline method. So it generates some random walks on the provenance graph, and using a skip-graph model, it provides some embeddings for each of the node in the graph, and then you can later fit those embeddings into a downstream machine learning task. And this is, let's say, like another one that we use. I actually use this one as for the later task. I use the self-supervised learning-based embeddings instead of node to wake, and compare the results. If you are curious to see how it works, and you can go to our paper on this. So to evaluate how it actually works, then the node to wake method, we used multiple machine learning models, and we used tenfold cross validation. We had 70 to 30 train test split, and I had like 3 different evaluation methods. First was binary classification, basically saying that this node is attack or is not, is benign. Multi-class classification, the model should also say that which subcategory of attacks this node belongs to. And correlated attack stage classification is for be able to actually understand what stage of attack this node belongs to. And the important evaluation metrics for us here is recall and Erfan score. So you can see the results of node to wake embeddings here. This is for the binary classification, and this is for the multi-class classification. You can see the accuracy is pretty high here, but the important metrics for us here is recall and Erfan score. You can see the results here for this table, and this one that is for the multi-class classification. And the final evaluation metric for us is the correlated attack stage classification result. We can see the result for each of the attack stages: collection and exfiltration, CNC and credential access, defense evasion and persistence, and discovery and lateral movement. So this was my presentation on CIC APT IoT dataset. If you have any questions, you can actually type them in the chat, and Samit will ask them from me. Or if you had any other question, you can email me, and this is my email, and you can contact me using this email, and I'll be more than happy to answer your questions.
Thank you, Irfan, for this insightful presentation, and for all our viewers. If anybody wants to get in touch with Irfan to sort of have more insight on his presentation, his email was just mentioned in the last slide. Irfan, with this, we move on to the Q&A part of today's session. Let me just see if we have any questions in the chat session. So the first question is, Irfan, how did you simulate the low and slow approach in your simulated APT?
That's a very good question. Thank you, Sumit. So the thing, as I mentioned, one of the important characteristics of APTs is that they use a low and slow approach. They're not constantly attacking the targets. They try to remain undetected. So how we did that was that we had a attack emulation plan consisting of more than 30 different techniques, but we didn't execute them one by one, just one after another. So we just had them randomly span through like a 3-day period. So basically, it's not as long as a real APT, but we try to have those approach, and our attacks are like in the case of time, they are distant from each other, and you cannot detect them just by using the time. So that somehow simulates how an actual APT scenario works.
Okay. Thanks for that, Irfan. Our next question is, why are you using recall and F1 score as your main evaluation metrics?
Very good question. That's actually somehow related to the previous question. So as you saw in the slides, the data sets that are related to APTs or advanced persistent threats are highly imbalanced. So you did have like about 53,000 benign nodes, and you had like only 300 attack nodes. So the thing is, when you have a highly imbalanced data set, having accuracy as your main measurement metric, it can be misleading. So because for whatever machine learning or deep learning model that you develop, you can have more than 99.9% accuracy. So it's not going to be helpful. The important thing for us here is to be able to actually detect those attack points, detect those attack nodes. So that's why we use mostly recall. What recall shows us is how successful we were on detecting those those attack nodes and the graph in the provenance graph. So that's why we use recall, and after that F1 score as our main evaluation metric.
Okay. Thanks for that, Irfan. With this, we move to the next question in today's session. Why did you use a network simulator to connect different components of the test bed? And then the second part of the question is, what were the advantages of this compared to directly connecting them?
So the reason that we used a network simulator, it was NS3, as I mentioned. The reason we used NS3 to connect different components to each other, and we didn't directly connected them to each other, was that we wanted to have a full control over the components and what happens inside our network. So because all of the connections was made through the NS3, and was so that way we had a complete control and complete monitoring capabilities over what happens in our network. So if device 1 sends some packets to device 2, we can easily capture those things because it happens in our simulation, in our own simulation, and it happens in NS3, and using NS3 we can capture all of the packets that we need. So that was the main reason. We could also connect them directly, but we didn't have this extent of control over the packets, over the components, over the network that we had when we are using NS3 for.
Okay. Thanks for that, Irfan. It does certainly give a good explanation of the question. So with this, we move on to the next question. How do you think that this research can add insight to the cybersecurity of industrial applications?
Thank you. It's also a very great question. So the thing is, as I said, we do have a lack of comprehensive data set that somehow represent this scenario that we were looking for. So we do have do not have enough data set that provides some aspects of like industrial IoTs and also APTs, and these are very important things. So, for example, most of the data sets that are out there are like focusing on different type of attacks, for example, DDoS or DOS or attacks that are very important when we're dealing with the IoT or industrial IoT. But there are not like too many data sets that would be helpful to detect actual APTs. So what we wanted to show with this data set and we wanted to help was to help the community, help the researchers when they are dealing with APT scenarios. The other thing that we wanted to somehow influence the literature, influence the community about it, is that how using and how to having the provenance data in the data sets and how to using the provenance data can actually be very helpful in detecting some types of attacks, such as those APT attacks that I was just talking about. We don't have that many data sets that have provenance data and provenance graph in them. So we hope that this data set that we publish somehow helps the researchers that are trying to have the provenance graph, have provenance data, and use those provenance graph and data to detect APTs.
Understood. Thanks, Erfan, for this very clear explanation of this question. With this, we'll move to another question which reflects on what was the motivation behind this particular dataset. So I'll just read the question. What motivated you and your team to create this dataset, and how does this address gaps in existing APT datasets for IIoT?
As I mentioned, because industrial IoTs are being integrated into critical infrastructure, any attack or any disruption in those settings in the industrial IoT can have high impacts. I provided some of the examples, for example, attack on a Ukrainian power plant. And because of that, that's actually very impactful, and that's actually very hard to detect. So what motivated us was that we were trying to prevent those kind of impacts into critical infrastructure in the manufacturing sector, in the energy management sector, in the, logistics and transportation sector. We know that anything that happens to an industrial IoT in an IIoT setting can be very dangerous for the community, can be very dangerous for the industries. So we are trying to help people to help in this sector, and we're trying to prevent those things. And what was the second part of the question? Sorry.
The second part of the question is, and how does it address the gaps in existing APT datasets for IIoT?
Yeah. So as I said, we do have a lack of the comprehensive dataset. When we were doing this research, we actually didn't have any data set out there that actually shows, represents the industrial IoT and also have provenance data in it. So that actually helps to provide some materials and put that on the gap of this particular gap in the research. That's what I think about.
Thanks for that, Erfan. With this, we'll move on to the next question. As a seasoned expert, what are the challenges around creating some of those data sets. Sometimes we have challenges around collecting data and then the quality of the data. So this question is sort of asking those questions. So what challenges did you face in collecting both the provenance and the network logs in a synchronized manner?
Yep. Thank you. So one of the challenges, one of the most important things when you're generating any type of data set is that the data set should be useful. It should be the people in academia and people that are doing research should be able to use that data set. And for that, you need to have your data set as realistic as possible. The data sets that are completely unrealistic and don't have to do anything with the real world scenarios are not going to be that much useful. The other thing is that you should be able, as you mentioned, you should be able to synchronize the collection of provenance graph, provenance data, network logs, host logs, everything. So for that, you need to have full control over the system, over the network, and you need to be able to synchronize this collection of data. That's another challenge. Another thing that I think was very important is what approach you are choosing in order to be able to label the data. So, for example, I didn't mention that because of the lack of time, but actually labeling the provenance graph was very important and was pretty challenging for me because I had to use process IDs and PIDs and PBIDs for that. And with that, I managed to have a solid labeling solution for that. So yeah, that was some of the challenges that I faced with generating the data set.
Thank you, Irfan. This was the last question in our today's segment. With this, we come to the end of today's session. I certainly had a good time. I enjoyed, listening to all the presentation. We covered some different topics around IIoT and IoT, and we also, covered the malware analysis with respect to the topic. And with this, we will be signing off now. If you're a student, if you're a researcher, or somebody who wants to understand more about the cybersecurity space, the best way to reach out to us is through our LinkedIn channel. So with this, we will be signing off. Thank you for all who have joined us today, and thank you to all our speakers of the day. So thank you.